So this is a really scary looking set of notes. But what it allows us to do is turn really ugly limits into really simple ones. And this starts off with two very basic limits. The first is that of a constant function. A constant function is one that always has the same value. So in this case, k is a number like 2 or 3 or 4. And this is the idea that if your function never changes, it's always going to have the same limit. So an example of a constant function would be something like y equals 2. Let's make it green. It doesn't matter what x value I care about. It doesn't matter if I'm talking about a left-hand limit or a right-hand limit. Nobody cares. The limit of this function as x approaches c, an x value. I don't even care what x value. The limit of this function is just going to be 2. So constant functions are boring. A constant function is going to have whatever value k is. So the limit as x goes to some value c of that function is just k. So that's sort of whatever. And then the other really boring function is f of x equals x. So if we pull all this over real quick, f of x equals x is our boring identity function. It's just a line going up at a 45-degree angle. It's got the points 1, 1, 2, 2, 3, 3, so on and so forth. So this one is a slightly more interesting limit, kind of. As x goes to c, whatever value c is, the limit of this function is going to be c. Note that I forgot that too last time. Is going to be c. So in other words, as x goes to 3, y is 3. As x goes to 4, y is 4. So this function is also kind of boring. Limit as x goes to c is going to be c. So using these two rules, and all of these other properties, we can turn really ugly limits into really simple ones. So I want to look at these properties just momentarily, and then we'll use them and hopefully see that they're not that big a deal. Most of these properties are things that we expect. The limit of a sum or a difference is just the sum or difference of the limits. In other words, you can break a limit up over addition or subtraction. It kind of looks like the distributive property. It's not the distributive property, but I wouldn't fault you for calling it that. However, limits also can be broken up over products and quotients and powers and radicals. They're the nicest operation we've pretty much ever dealt with, ever. So note that you can move the operations around pretty much at will. So you can turn a really ugly limit into a series of really simple limits. The one last weird one is the scalar multiple. Notice if I have something like k times my function, that k comes out as if we're factoring. So again, distributive property factoring, not really the correct terms here, but the idea still holds. You can pull scalars out. A scalar is just a constant, some number that we're calling k. And we can also break limits up over our standard operations, sum, difference, product, quotient, power, and radicals. So I'm only going to look at one of these. I'm only going to look at one of these because it's not so much that we use the properties as what the properties mean for us, how they make our lives easier that I want us to see. But 2 is the one that I really want to focus on. Because right now, that's one of those limits that, like, I can't do that in my head. I would have to graph. I would have to use a table. But this section's all about how can I use algebra. So I'm going to do this problem the long way, and then we're never going to do it the long way again. So if we look at what we have, well, according to all of those properties, I have quotients, I have sums, I have differences, I have a power, but I can break limits up over all of that stuff. So I'm going to let limit be blue here. So in other words, I could rewrite this as the limit, and I'm going to avoid that whole x equals 5 for a second. I can break that up as the limit of x and the limit of 1, all in the numerator. And, then I can do limit of x in the denominator. And, oh yeah, by the way, that's squared because of this square, minus the limit of 3. So what I did there, at first glance, it looks like I just took that limit and applied it to everything. Well, you wouldn't be wrong if you thought that's all I was doing. So now what I have is a bunch of constant functions and some identity functions. So everywhere I see a limit of x, I can replace that x with 5, because that's our identity limit. And everywhere I see a number like limit of 1, I can replace that with just the number 1. So I can replace this with a 5 and this with a 5. And I can replace this with a 1 and this with a 3. Well, that's nice, because that's just going to be 6 in the numerator. And 5 squared is 25, take away 3 is 22. And 6/22, well, that's just 3 of these. This will be the last time I ever do this all the way through, actually rewriting the word lim for each one of these substitutions. Note that effectively what this allows me to do is break an ugly function down into its component parts and just substitute. It's kind of nice. So I want to go ahead and get to the point here, and the point is this. You can simply substitute whatever your x value is into well-behaved functions. And what a well-behaved function is, that's the kind of function we like. The ones with domains like all real numbers. Ones that don't have holes or asymptotes, in particular vertical asymptotes. So usually we're thinking polynomial functions like quadratics, cubics, stuff like that. So when you have a nice cubic function, you can just substitute that x value into the function to find the limit. If you have a discontinuous function, sometimes substitution works, and other times it does not. And we're going to look at examples of both ones that do work and ones that don't. So that's really the meat of this section. When are you allowed to substitute, and when does that break down and you have to worry about other tactics? So we're going to go ahead and start right here with number 7. This is the real meat of this section. Now, I am still a huge fan of letting robots do the robot work. Just because we're doing algebra here doesn't mean the calculator should go away. If I want to know if this limit exists as x goes to -2, well, I can just pull out my calculator. Now, if you think you're working with a function that you're going to need for a couple of steps, it can be worth it to put that function into your calculator. I will go ahead and do that since I've already started. In this case, this is a function we're going to answer one question on and then never use it again. So whether it's worth your time to store it is up to you. If you wanted to look at a graph, you certainly could look at a graph. If you wanted to look at a table, you certainly could look at a table. But the purpose of this section is to stop looking at tables and looking at graphs, and instead just substituting the value in. Can I just take that -2 and substitute it in? Let's find out. Sure can. So because we're talking about a cubic function here, yes, we can evaluate this using direct substitution, and the limit is 19. Yep, that's it. Let's take a look at 8. Taking a look at 8 right now, notice it's rational. So we know that there's going to be some kind of issue there. Go ahead and clear off this screen. We know there's going to be some kind of issue there, and instead of storing this function, I'm just going to go ahead and directly substitute. So note that I would have a 1, because I want to know the limit as x approaches 1, plus 5 in the numerator, along with a 1 squared minus 1 in the denominator. Now, before I hit enter, you should all be like, wait, that's illegal. And sure enough, it is undefined. Because we have that 1 minus 1 in the denominator, this is not a function that we can use direct substitution on. So we are going to need a different method for this function. It cannot be evaluated by direct substitution. So for now, we're done. We will play around with this idea a bit more later, because there are things that we can do to fix that. But for now, nope, cannot find that limit. Take a look at number 9 here. With number 9, this one isn't so bad that we really need the calculator, so let's just go ahead and do it. We have 16 minus 1/2 times x. X in this case is 10. Now, radical functions are not as well behaved as polynomials, but this is going to work for us. Half of 10 is just 5, so this is the square root of 16 minus 5, which is just root 11. It's an ugly limit, but that is our limit. So yes, yes should really be green. That makes me much happier. So yes, in number 9, we could use direct substitution there. With number 10 is going to be another one that will not work. It's not going to work for us. I can go ahead and tell you why right here. Notice when we substitute that -5 into the bottom, we're going to get a 25 minus 35 plus 10, which is going to be division by 0. Because 25, take away 35 is -10, plus 10 is going to give us 0 in the denominator. So 10 doesn't work either. Let's look at a few uglier functions. Oh, this video is already dragged on, so I'm going to go ahead and put a stop here, and we'll jump back to number 11 next time.